Hello guys, welcome to lecture 3 of waves and oscillation lecture series. We are discussing waves. So in the last two lecture we discussed the following. So we saw in the oscillation part of the lecture series that there is an equation where we write y is a sine omega t. Okay, we studied this type of equation. So what is a sine omega t? This represented a particle undergoing a simple harmonic oscillation. What was the diagram for a sine omega t? So let us do that. So you have s- y is the displacement of the single particle, okay, from the mean position. Say this is the mean position, and t is the time. Okay, so what happened to the particle? As the time went, the particle goes from mean position to an extreme position, comes back to the mean, goes to the other extreme, again comes back to the mean, and this continues. Okay, so this is related to oscillation. And next we studied about an equation where y was a sine kx, and we said that this particular equation it does not represent a wave, because no doubt it makes a wave like structure in space, but it does not give the wave any motion. So what kind of things we are looking? So y is the displacement in this direction and x is space. Okay, so if we imagine that there are small particles, so the entire rope is made up of infinite number of small particles placed very close to each other, then y is equals to a sine kx represents a wave where the particles are in this manner. It means various particles have various displacements. So a particle here has this displacement, the particle here has the maximum displacement, which is the a, and this particle here has a very small displacement. This particle here has a maximum displacement in the other direction, okay, and so on. But this did not represented a wave, so this is of no use. The third equation that we studied that actually represented a wave, because it allowed the motion of the entire wave like structure. So what was the third equation? A sine kx minus omega t. So introduction of a minus omega t into the sine kx made the entire wave move. So let us see. So this would represent the same thing. Okay, so let me bring this diagram again, because both are same thing. Okay, represent this. But interesting thing about the third equation is that it makes this particular thing move with time. So as the time goes, the entire wave moves forward. Okay, now I said wave is nothing but a collection of oscillation. Now why I said that? Okay, so let us take a close look at the oscillation equation first. If you look at the oscillation equation first, then on the left hand side you have a y. Y represents length, okay, because y will be either in centimeter or meter or smaller than that. Y represents length. If you look at the right hand side, a has also the dimension of length. Okay, you have to agree with me on that part. A also has the dimension of length, but this sine omega t, so let me write length. Okay, but the sine omega t, this will have just a number. Sine omega t is just a number, it has no units. So both side we have the unit of length. It means y represents some kind of displacement. Displacement means the unit is in terms of length. So what is this displacement y? This displacement y, so if you have a particle, then from the mean position, how much up the particle went at a particular time, or how much down the particle went at a particular time, that is represented by y is equals to a sine omega t, because the entire displacement is dependent on only time. Agreed? And there is no space part here. Okay. Similarly, in this equation, if you look at this equation carefully, this y here also has the unit of length. Agreed on this part? This a here also has the unit of length, and sine kx minus omega t is nothing different. This part is nothing but an angle which will be in radian, and the entire sine of an angle is just a number. So this has no unit. So you can see that the y that we are dealing in the wave is also a kind of displacement. Agreed? But there is something special with the wave. Okay, so let us see what is the special thing about the wave. So let me make a big diagram to make you understand what is so special in a wave. So you know what happened. So if you have a rope, so consider this black line, this one is a rope. Agreed? So you can imagine a rope made up of tiny small particles, infinitely small, and they are very close to each other. So all these particles are very small. So you can imagine the rope to be made up of small particles. So when you make a crest and trough in a rope, so this, look at this big red line. So let me red circle, let me write this as O, the particle at O, and look at what happens. So when you shake the rope, all the particles, so this side you have the y displacement. Okay, initially all the particle had the position y equals to 0. It means all the particle had the y component 0. All the particle were at rest. And this side we have the space x. So when I consider all the particle, it means I am considering all the particle at various positions in space, because the entire rope is made up of small tiny particles. Okay, you can imagine the rope to be made up of tiny small particles. So these are represented by, say, this red dots. Agreed? Now can you tell me what happens when you shake the rope? All the particles, they assume some particular displacement. So you can see I'm making the displacement diagrams of various particles. Okay, so when you shake the rope, various particles assume various displacement in the y direction. So the rope looks like this, and the particles on the here will look like this, because all the particle on this position and this particular x, they go in the other direction, they have displacement in the other direction. Okay, and in this way a wave is formed. So how a wave is formed? So when you look at a rope that looks like this, so the black rope, so consider, forget this, so now the rope looks like this. Agreed? Because you have generated a crest and a trough on the rope. So what is happening here? All the particles have gone up, but how much up, that is decided by this equation. Okay, so what is y is equals to a sine kx minus omega t? Let us see. Okay, so this equation says what is the displacement of a particle which is at position x and at a particular time t. This is what y is equals to a sine kx minus omega t tells you. So let me repeat again. Y is equals to a sine kx minus omega gives you the information of the displacement of the particle from its mean position at time t, and the particle is present at the position x. So for example, consider a particle is here. So what is x here? Very cleverly, you know this x will be 3 lambda by 4, if you assume that this part is lambda. Agreed? So x means which particle are you considering, where the particle is lying, and t means at what time are you considering, because if you change the time, this wave will move forward with time and the entire displacement is going to change. Okay, for example, after a particular time, how this wave is going to look, let's see. Okay, I'll make a diagram here. So again, this is a black rope, and this is the y direction, that is the displacement in y direction. X means various positions in space. So after a particular time t, so say consider you have generated a crest and a trough, then you see that after a particular time t, the displacements are like this. What does this mean? This means that the particle which was initially at O, in the first part you see the O is there and everything else was shaking, and then after a later time the displacement of the O went down. Okay, so the displacement changed with time, and this particular position this particular position is what? X is lambda by 4. So the particle at lambda by 4, which was initially, because of the generation of crest and trough, was at a displacement a, now it has returned to its original position O. I mean y equals to 0. Now is in the mean position. All this happened after a time. So what will be the time? I guess it will be t by 4. So after a time t by 4, you see that the displacement of various particles at various positions has changed with time. Okay, so I hope you understand what this information. So the wave equation carries the information of the displacement of various particles at position x and at time t. Okay, now let me make you more clear that it really is the displacement. Okay, let me give you a hint. If you look at this equation carefully, okay, at time t equals to 0, now say let the time happen, let the time is there, and look at the particle at x equals to 0. Look at the particle at x equals to 0. If you look at the particle at x equals to 0, then the particle at x equals to 0 obeys the equation minus a sine omega t. So if you ignore the minus sign for a moment, which just represents the direction in which the displacement is happening, then you can see that the particle at x equals to 0 is following a simple harmonic oscillation equation. Look at this. So the wave equation for the particle at x equals to 0 just looks like the equation of oscillation. Look at this equation at the top. Can you look at this? So what is this equation represent? This equation represent the oscillation with time. It means the simple harmonic oscillation of a particle with time. And this shows that the particle at x equals to 0 for any time t is moving with a simple harmonic oscillation. It means the particle here will go down. Okay, each of the particle on this rope, each of the particle on this rope will undergo a simple harmonic oscillation with time. They move up, they go down to the mean position, they go to the other position, again they come back to the mean position. In this way all of the particles, they go up, then come down, then go to the other position, and then comes to the mean position. So consider any particle on the rope, and you find that these particle, they will undergo a simple harmonic oscillation. It means the wave equation carries the simple harmonic oscillation of all the particles which are on the rope. And where is the information of all the particles? The information of all the particles is at x, because various values of x will take into consideration various particles, and the motion, the simple harmonic motion of various particle information is carried in the omega t, because you have seen omega t coming in the oscillation chapter that we have already discussed. Okay, so I hope you understand this. So I'm going to repeat one more time the same statement. A wave equation carries the information of the displacement of each of the particle on the rope, which is at a distance x from the origin and at a particular time t. Okay, that's why I have written this wave as a collection of oscillation. It is a collection of oscillation, and the wave equation, it is a simple harmonic oscillation for various particles at various position. Nothing big. Okay, so always remember the equation of motion of the wave, I mean the wave equation, the y is equals to a sin kx minus omega t, always represent a particular displacement. It does not represent any wave. As you can imagine, it represents a displacement. And when you look at all the displacement, you feel that a wave is generated and the wave is moving with time. Okay, so I hope you understand this lecture. We'll discuss more on waves in the next lecture.